Hmm? Energy according to this is now, according to this, is nothing but summation of this up to infinity or a finite number of n. And if all of the signals are taken for n number of approximation in the same orthonormal set, then one signal differs from the other signal in terms of the location of the point, but where the point is going to be located is the same energy point, which means the radius of the sphere will remain the same. So, all the signals will lie on the surface of a n-dimensional sphere. It is easy to see if the 3-dimensional sphere, so you will be on a 3-dimensional sphere point on that. In general, for a more complicated signals, then you will end up into an n-dimensional sphere, and on the point on an n-dimensional sphere, all of them will have the same amount of energy, except the actual function differs because of this xi being the different. So, it is a beautiful way of converting a continuous time signal in terms of a vector representation, in terms of a set of numbers, and whole of communication theory has developed based on this way of looking at signals. Instead of looking signal as a function of time, look at signal as a vector. And very fundamental results have been obtained, and many things in communication theory like estimation and coding or estimation or extraction of signals from noise, all this have been done based on this way of looking at the signal. Amos-Shannon theorem, which you will come across maybe in this course or next course, on which the whole of confirmation theory, communication theory has been developed. We very simply look at this by saying that the signals are on a n-dimensional sphere and found out that relationship which change the whole thinking in the area of communication. Very easy to prove that, we will do someday. So, this is the representation of signals in terms of the vector spaces. Now, let us look at what phi do I choose, right? Ask the question, is the phi set unique? Then nothing about the phi set. For there may be many orthogonal sets on this domain which will have orthogonality, orthonormality, which is in your hands, and you can represent x of t in terms of any one of those. Among this, which one would you choose? Right? It depends upon your specific interest in a given problem. For example, I would like to choose this function as the eigenfunction of the system. I am sure you know what is eigenfunction, eigenvalue in mathematics, and we did it in 101 also. What is the beauty of the eigenfunction? With respect to system or a network or whatever we have seen, eigenfunction is, if I put in that eigenfunction as input, the output will also be the same eigenfunction, except the amplitude will be different, right? So, the beauty of this eigenfunctions is that if your input is expanded in terms of eigenfunctions, the output also is equivalent to summation of same eigenfunction, except the level of the eigenfunctions are changed. So, I would like to choose this phi it's as equal to eigenfunctions of the system to which this is the input. If I have black box, we will come to that later. If I have black box and I am given a signal x of t, and I want to find what is y of t, the best thing for you would be to expand this x of t in terms of eigenfunctions of this class of black boxes. If it is a linear time invariant system, we have found out in 101 the eigenfunctions of these are exponent sinusoids, e to the power of st or e to the power of j omega t. So, we would like to expand this in terms of e to the power of j omega t if this happens to be a linear time invariant system. And this is the reason we are all so carried away by sinusoidal analysis. If this any characteristic of you change here, the linearity or time invariance, then obviously sinusoid is not the best signal to use. If there is a time varying system, linear time varying system, it turns out that some polynomials called Laguerre polynomials happen to be the eigenvalues. Some other class of signals, systems, maybe some other thing is a eigenfunction. But the moral of the story is that I need to expand this preferably in terms of eigenfunctions of the system on which the signals are being applied. Then analysis becomes easy for you. It is not that if I always use sinusoidal, I can't analyze it. Surely I can analyze it. Any system I can analyze. But maybe it doesn't make sense. If you take a nonlinear system and apply sine waves to input to analyze it, then nothing much information you get out of it. So these are the kind of things. So the phi i's must be some naturally related function to your problem. And the logical thing for you to do is to choose this phi I t as the eigenfunctions of the system. We will discuss later again what is this eigenfunction of a given black box, how do you find them and all this. But we have some background in the 101 where we discussed linear time invariant systems and proved that the eigenfunctions of this from this state equation and eigenfunctions are exponential functions in general like e to the power of st, with s having a negative real part. Remember all this on 101? Okay. So what we need to do to find out xit, I have written there. So what do we do? If you are an engineer, how do you find x of t? Mathematicians will write this equation, but if you are asked to go to lab and find out its exercise, what will you do? You just look at this integral. It just says put x of t as an input, multiply it by locally generated phi I t, right? That's what this is. And integrate this product from 0 to t and out comes your x of I. Same mathematical equation I represented now in terms of a hardware. So you have an analog multiplier which we studied in electronics, a time function multiplying by another analog time function as a difference amplifier or something like this in a analog multiplier mode, and take this one and integrate it over a period of time 0 to t. And what is that we do? We operate an amplifier with a capacitor in the output to input feedback, and then you see it at time t is equal to t, the value of x. So it's very simple for you to find out what this x of i's are. This way of finding xit is what is known as a correlation type. And all your communication receivers apply this principle to find out what is the signal that is transmitted and get the information regarding what happens from input to output. I can also do the same thing with your knowledge in 101. I claim I can do the same thing like this. I put x of t through a linear time invariant system with an impulse response equal to x of t, and output will be equal to integral 0 to t, right, h of tau, x of t minus tau, d tau. By definition, the impulse response, in terms of impulse response, the output is in terms of the input. And if you now look at this, compare this equation with that equation, what all I am trying to do is to put a black box with an appropriate impulse response so that at the output of that I get a value of x of. It turns out if a hi tau is equal to phi I t minus tau, this response of this will be same as the what we are looking for. The impulse response is the same phi signal made left to right and right to left. So substitute this into this and find out what is the output of this. So what we do is we actually, for getting this t here, the same idea with a switch here, close the t is equal to t. Because upper limit has to be t. So xi you get. There are two equivalent ways of finding the values of xi corresponding to coefficient of a orthonormal expansion in terms of the hardware realization of the same equation that we written here. As a mathematical way of looking at it, this is my way of looking at it as an engineer.